अच्छा बेटा today is 3rd March 2026 and this is crash course on IGCSE physics. In the last class we have discussed the theory on electromagnetic induction and I taught you this is a coil of wire and consider this is connected with a galvanometer or ammeter or a voltmeter. Consider we have a bar magnet and the bar magnet is placed at a large distance from the coil. So the magnetic field lines produced by the magnet rod, sorry, the coil is at a large distance from the magnet bar. So no magnetic line, not cutting the coil. But if I move and insert this magnet rod into the coil, then obviously magnetic lines begin to pass through the coil. And you know, when magnetic line passing through a coil, there is a chain of magnetic flux, and this magnetic flux produces induced current in the coil. Induced current in the coil. Or we can say when a coil is cutting magnetic field lines, induced current is produced. And we have studied if the movement of the bar magnet is fast, then induced current, induced EMF, induced voltage is directly proportional how fast the magnet is moving. So it will produce greater EMF if the magnet is moving at a high speed. As well as we have studied in the last class Lenz's law. And according to Lenz's law, if the north pole approaching the coil, it will produce north pole here. If you move south pole towards the coil, it will produce south pole. Sir, why? Because magnet movement is the action and the coil will give you reaction. And reaction force is always in opposite direction. So when north pole approaches the coil, it will produce north pole. When south pole approaches the coil, it will produce south pole. And same pole repel each other. So it is according to Lenz's law. Okay, we have studied. So this is just a revision. And now we are solving a question. The question from May, June 2022, it is a new question. And we haven't discussed this question with Pavitra, with Atif, and with Ammar in the last classes because they are revising. And this is a new question, beta. Okay. Consider this is a magnet bar, cylindrical magnet bar. And this magnet bar, it will pass through plastic tube as well as it will drop through copper tube. So this is an experiment. Now we are starting experiment. One tube is made of plastic, the other tube is made of copper. The two cylindrical tubes have identical dimensions. I mean, it means their length is same, their diameter is same. We have a small cylindrical magnet, okay, but it is extremely strong. Initially, the magnet is at rest at the top of the plastic tube. Consider this is a plastic tube and consider this is the cylindrical magnet. And now the magnet is released and it falls through the plastic tube. And when it is passing through the plastic tube, it does not experience any resistive force. And if there is no resistive force, then it is called free fall motion. So the magnet is falling through the plastic tube as free fall motion, and you are given it is taking time 0.67 second to fall to the lower end of the plastic tube. You are given the mass of the bar magnet, and they are asking calculate kinetic energy. You know, kinetic energy equation is half mass and velocity is fine, sir, but we are not given velocity. We are not given velocity. So we should first calculate velocity. But Navia, can you help me? Do you know any equation which can be used to find out the velocity? When the magnet is dropped, its initial velocity is zero. But when the magnet is falling and hitting the ground, what will be its final velocity? Do you know any formula, Nevia? No, we are not given distance. We are not given distance. But Pavitra, do you know? And I think you should know, Pavitra. You should know. And I have taught you this formula. Pavitra, Pavitra, are you there? ये लो भाई. अच्छा जी. Actually, I taught you this equation, and this equation is called first equation of motion. V is equal to U plus AT. And actually, it is the modified form of this equation. You can use this equation as well, but its modified equation is this. And in this equation, sir, we are calculating final velocity is equal to initial velocity is 0. Time, yes, sir, we are given time. Time is 0.67 seconds. And if an object is falling down without any resistive force, then it is free fall motion. But Navia, what is acceleration of free fall motion? If an object is falling freely, then what is acceleration? Navia. Amar beta, if an object falling freely, then what is acceleration? Sir, acceleration is 9.8. It is known as small g. G is gravity. G is acceleration of free fall motion. 9.8 बेटा और you may write 10 लेकिन इतना लेट बता रहे हो बेटा जब तक मैं बता चुका हूँ. Okay, so you can use 10, you can use 9.8. So the final velocity becomes 6.7 meter per second. So this is called first equation of motion. V is equal to U plus AT. Everyone should know this formula. So first you should calculate acceleration, sorry, velocity by this equation. And now we have calculated velocity and now we are going to calculate kinetic energy. So kinetic energy equation is half and then mass and then velocity square. And then you can calculate kinetic energy. And the energy unit of kinetic energy will be joule. Note down beta this calculation. G Amar 0.269. पर यार ये बताओ कि अमार तुमने मुझे आंसर ये वाला क्यों नहीं दिया और इतना देर से क्यों दिया जब मैं बता चुका था. अमार भाई ये अच्छी बात नहीं है ना यार. अब आपको तो हर चीज में बिल्कुल एक्सपर्ट होना चाहिए क्योंकि हर चीज आप कंप्लीट कर चुके हैं बेटा. ठीक है. अच्छा चलिए जनाब, नाउ वी आर मूविंग फॉरवर्ड फॉर द नेक्स्ट क्वेश्चन. The next question is so the magnet, now the magnet is then held at the top of the copper tube, and you know copper is a conductor. It can conduct electricity, it can produce electricity, whereas plastic is an insulator. It cannot conduct current, it cannot produce electricity, but copper tube can. And now the magnet is falling through the copper tube, and you are given electric current is generated in the copper tube. Okay, this is a copper tube and electric current is generated in the copper tube. The question is explain why there is a current in the copper. Why there is a current in the copper? Actually, when the magnet, consider the magnet is here. Consider the magnet is here. This is a magnet rod. You know, magnet rod is generating magnetic lines of forces. And initially, no magnetic line is passing through the copper tube. But when the magnet bar falls through the copper tube, then the copper tube will cut magnetic field lines generated by magnet. And you know, when a conductor, when a copper tube cutting magnetic field lines, then induced current will produce. So I am writing the tube, copper tube is cutting magnetic field lines as magnet falls through tube. And you know it is called electromagnetic induction. And now they are applying Lenz's law. According to Lenz's law, the question is the current in the copper wire produces a magnetic field. This current is produced, okay, by copper tube. A magnetic field is produced in the tube. When current is produced, then a magnetic field is produced around the tube. And this magnetic field will oppose the free fall motion of copper tube, which is not present in plastic tube. That is why the magnet falls slowly in the copper tube. So the question is explain why. So if I start with Lenz's law, according to Lenz's law, according to Lenz's law, induced current, induced current opposes, induced current opposes the movement of or falling down the bar magnet or cylinder magnet. Cylindrical magnet or bar magnet is falling down, and according to Lenz's law, the induced current always opposes the cause. The cause is falling movement of bar magnet. So the induced current will oppose the falling movement of bar magnet. That is why it slows down. Whereas in plastic tube, no induced current, no Lenz's law. So in plastic tube, it was falling freely. So this question we have completed, and now another question. And in this question, May June 2022, sir, a spring. Consider this is a spring, and this is spring. Its lower end is connected with a bar magnet, and consider this is a coil of wire, and this coil of wire is connected with a galvanometer. Okay, and then this magnet will oscillate, move down, move up, move down, move up. Okay, and now read the question. The magnet on the one end of the spring coil connected to a sensitive galvanometer. The magnet can move freely through the coil. Okay, the magnet can move into the coil, out of the coil, into the coil, out of the coil. The question is the magnet is pulled down, and released. When you release the magnet, when you release the magnet, it is first pulled down. Pull down means initially the magnet is inside the core of the coil. And when it is released, then obviously it will move upward. And as it will move upward, sir, there is change of magnetic flux. Initially, the coil is cutting magnetic field lines. Initially, there is a magnetic flux, but when the magnet is moving upward, then there is a change of magnetic flux. There is decrease in magnetic flux. And this decrease of magnetic flux, it will produce induced current. So the galvanometer showing deflection. So I am writing as magnet moves upward, there is change of magnetic flux through the coil. Through the coil, there is a chain of magnetic flux. And this chain of magnetic flux produces induced current. So galvanometer, galvanometer needle shows deflection. The pointer, this pointer is called needle. This pointer will show deflection. When current is produced, then the pointer or the needle of the galvanometer shows deflection. So the key word is, sir, when the magnet is pulled down and it is released, the magnet is moving upward. And when the magnet is moving upward, there is a chain of magnetic flux. And the chain of magnetic flux, it will produce current, and this current will produce deflection in the needle of galvanometer. And now they are changing. So what is changing? The magnet is replaced with a stronger magnet. And if stronger magnet is used, then the question is what happens to the needle of the galvanometer? So the answer is, sir, when stronger magnet is produced, then greater induced current will produce. And when greater induced current will produce, then they are asking what happens to the needle of galvanometer. So if the magnet is weak, then the deflection of needle is small. If the magnet is weak, a small current is produced, so the deflection will be small. But if the magnet is strong, then greater current is produced. And when greater current is produced, then the needle will show greater deflection. Needle will show greater deflection. And it is a 1 mark question, so we do not need to write in explanation. Just give the result. The result is uh, greater current produced. So needle will show greater deflection. Needle will show greater deflection. If the magnet is weak, if the magnet movement is slow, then current is small. If the magnet is strong, if the magnet is moving fast, then greater current is produced. When greater current is produced, then the needle will show greater deflection. So this question is completed. And now the next question is not about this topic. This is about transformer. And transformer, I think we will study tomorrow. So I am ignoring this question. And now another question. So it is October, November 2019 question. Consider this is a ground. Consider this is a slope. Okay, this is a slope. And on this slope, we have a magnet, and this magnet is placed on a trolley, a small trolley. Okay, and consider this small trolley is released from this point. Consider, when the small trolley is at a large distance, then obviously no magnetic line is passing through the coil. When the bar magnet on the trolley is at a large distance from the coil, then there is no magnetic flux. Coil is not cutting magnetic field lines. But when the magnet is released, now read the question. The magnet is fixed on a small trolley that runs without friction on the track. Now the trolley is released from point A. Okay, it is released from point A. Ignore my example. Now it is released from point A, and now it is running through the coil from right to the left. And the question is, what is observed on the galvanometer? And galvanometer having a needle, galvanometer having a pointer. So the question is, what is observed on the galvanometer? State and explain. And it is a 2 mark question. So I am writing, sir, the magnet entering, as the magnet entering into the coil, so there is change of magnetic flux, or the coil is cutting magnetic field lines. The coil is cutting magnetic field lines. There is a chain of magnetic flux. It produces induced current, and when induced current is produced, the keyword for the galvanometer, needle of galvanometer will show deflection, will show deflection. So the question is this, sir, what is observed on the galvanometer? You know, galvanometer is composed of needle. The reading is represented by a needle. So they are asking what is observed in galvanometer. It means they are talking about the needle. So the needle of the galvanometer showing deflection. When induced current is produced, then obviously needle showing deflection. And now the question is, the trolley is now released from point B. Okay. Initially, it is released from point A, and now they are changing the position, and now they are releasing from point B. You know, when it is released from point A, it enters at slow speed. It enters at slow speed. But when it is released from point B, so from point B, then the speed of the trolley will be faster. And when a trolley or magnet enters into the coil at a faster speed, there is greater chain of magnetic flux. There is greater induced EMF. There is greater induced current. And when there is a greater induced current, then obviously the deflection will be greater. The deflection will be greater. So the question is the trolley is released from point B. It runs through the coil from right to left again. State what is observed on the galvanometer and explain why it is different to the answer in A1. Okay, so I am answering. I am answering. So the answer is now magnet enters at high speed. At high speed, so greater induced current produced, greater induced current produced, and now needle of galvanometer will show greater deflection, greater deflection. When the speed is high or the magnet is stronger, greater current is produced. When large current is produced, then the needle of galvanometer will show greater deflection. And now the next question. In the next question is very simple question, but I am asking with Atif so that I can check he is in class or not. Atif, beta, are you there? Atif, beta, suggest a metal from which the magnet is made. Oh my God, you are wrong. Electromagnets are made of iron. This is a permanent magnet, and permanent magnet is made of steel. But you have made mistake earlier. So the answer is steel. And now the magnet is moved to the left. The magnet is moved to the left. Okay, it is moving to the left. And inserted a small distance into the coil. The galvanometer deflects briefly and shows there is a current in the coil. The question is why there is a current. So I'm not writing answer because this is the same type question. It is a third time. So when the magnet is entering, there is a chain of magnetic flux, and the chain of magnetic flux is producing induced current. I'm not writing. As the magnet is moving near to the coil, and Q of the coil behave as a magnetic pole. Magnetic pole. Navia, it is your question. Can you tell me which magnetic pole is produced? State the polarity of coil Q. What will be which magnetic pole is produced at this end? Navia. Yes, you are right. When North Pole is approaching the coil, it will produce North Pole. This is the statement. This is the statement. So North Pole is produced. And now, Navia, can you explain why North Pole is produced? Why North Pole will produce? According to Lenz's law, no, no, no. According to Lenz's law, you should refer, sir. According to Lenz's law, and now you can write the statement of Lenz's law. Okay, you can write according to Lenz's law, induced current, induced current flows in such a way to oppose the movement of magnet. Obviously, if the North Pole is bringing close to the coil, here it will be North Pole by the current, and this North Pole will oppose, repel, it will repel the forward motion of bar magnet. So it is according to Lenz's law. Okay. And now the question is, state two ways in which the deflection of galvanometer can be reversed. So I think I can ask this question with Pavitra. Pavitra, beta, we are interested to reverse the deflection of galvanometer. Consider when the North Pole approaching the coil, consider the galvanometer pointer deflect towards the right side. Can you suggest me in two ways what can we do to produce deflection in opposite direction? Pavitra, what should we do? We are interested to reverse the direction of deflection. We are interested to reverse the deflection. We are not interested to decrease the deflection. Increase and decrease deflection by strength of magnetic pole. Okay, magnetic field. Right now, we are interested to reverse the deflection. Pavitra, what should we do? We are not sending current. We are not sending current. How can we reverse the current direction? We are not sending current. Pavitra, you are not right. Answer me. Another way. G. Atif, can you answer? How can you reverse the deflection of galvanometer? Sir, in this example, the north pole is moved towards the coil. Okay. Conversely, conversely, north pole should move away from the coil. North pole should move away from coil. Number one. Number two, north pole is moved towards the coil. If you move south pole towards the coil, you can reverse the polarity of the magnet. You can reverse the polarity of the magnet and now making the same direction movement. So south pole should move towards the coil. So we can make these two changes to produce deflection, reverse. Deflection, reverse. The question is deflection, reverse. So you can change the direction of North Pole, and you can reverse the direction, you can reverse the polarity of magnetic pole. And now another question. The question is, there is a magnet, the magnet is already inside the coil, and now the magnet is pulled horizontally to the right at constant speed. The question is, what happens to the galvanometer reading? You know, sir, as the magnet is moved towards right hand side, there is a chain of magnetic flux. It will produce induced current. And the question is, what happens to the galvanometer reading? So the answer is that the galvanometer pointer will shows deflection. But in this question, they are asking as time passes. As time passes means, is it possible that deflection will remain constant? No, no, sir. The deflection will be only for for a second, for a very small period of time, for an instant. For an instant, galvanometer pointer shows deflection for an instant, and then returns to zero. Okay, so when the magnet is moved just one time, then the deflection is only for an instant. Okay, but if you keep on moving the magnet in out, then there is a constant chain of magnetic flux, and if the magnetic flux is keep on changing, then current is producing continuously. And now the second part, as the magnet moves, a north pole is produced at the left hand end of the coil. Okay. Now read this question carefully. Okay. Read this question carefully. It is not simple. The magnet is moved. The magnet is moved in this direction. You are given this direction. Then you are given. So the left hand side of the coil produced north pole. Produced north pole. Explain why the pole at the left side is north pole. So I am explaining. I am explaining. According to Lenz's law. According to Lenz's law, right side, right side becomes right side of coil. Right side of coil becomes south pole. Becomes south pole to oppose the motion of magnet. You can see the magnet is moving towards right hand side. If the magnet is moving towards the right hand side, if the magnet is moving towards the right hand side, then obviously this end becomes south pole to attract the movement of magnet. It becomes south pole, and if this side becomes south pole, then obviously the other side becomes north pole. Then obviously the other side becomes north pole. And now the next part is about transformer, which we are not interested today. And now question number 103. Suggest a metal from which bar magnet is made. It is steel. So the bar magnet inserted are the same type question. Same type question. We should not solve. We should not solve. This topic we haven't studied. This is not a EM induction topic right now. And now this is a question. This is another question. The question is 106 question. The lower end, the lower end of the magnet is pushed down into the upper end of the coil, held at rest. During the movement of during the movement, induced EMF is produced in the coil. The meter shows deflection. Why EMF is produced? Sir, old question. Old question. We should not solve this question. But I think this question, I think explain. I should explain. The explanation is the North Pole at the bottom, the South Pole at the top. Okay, you are given this situation. The magnet is released and it falls through the solenoid during the initial stage of fall, mean when the magnet entered into the coil. When magnet entered into the coil, the ammeter shows deflection to the left, to the left. Okay. The first part is very simple. Why ammeter shows deflection? So, sir, we know when the magnet is cutting the coil cutting magnetic lines, induced current is produced. So I am leaving A part, but I am interested in solving B part. When the magnet passes the middle point of the solenoid and continues the fall, it reaches the position Y. It reaches the position Y. Describe and explain what is observed on the ammeter as the magnet falls from the middle point of the solenoid to the position Y. G. Pavitra, can you answer me? When the bar magnet enter, the deflection is towards left side. But when the bar magnet crosses the middle point, what is observed? What is observed in the ammeter when the magnet fall middle point of the solenoid? G. What is observed in on ammeter? Pavitra, but can you answer? Pavitra, but can you answer? Navya, but can you answer? Yes, yes, number one. You are right. Sir, when it is entered, then obviously it is slow. When it is slow, then there is less deflection. You are right. And when it crosses the middle point, then obviously its speed is quite fast. And when it is at the bottom, it will be fastest. When it is fastest, then there will be greater deflection. This is number one. It is a 4 mark question. So not only greater deflection, but also there will be something different. Ji Nevia, one more different thing will happen. Nevia, can you answer? Your first answer is right. There will be. Bole? Yes, it will be opposite in direction. Deflection will be opposite. Deflection towards the right. Deflection towards the right. Why? Because initially it was entering the coil and now it is leaving the coil. And when it is leaving the coil, then the deflection will be reversed. The deflection will be reversed. So I am answering. The answer is as the speed of magnet is increased, so greater current produced and greater deflection greater deflection to the right as it is leaving coil. Sir, initially it was entering. The magnet was entering. When the magnet is entering, the deflection is to the left. But when the coil is leaving, then the deflection will be right. So the keyword I am highlighting is a deflection to the right, and there will be greater deflection. Greater deflection due to the greater speed. When the speed of the magnet is increased, when the speed of the magnet is increased, then obviously Greater current, greater deflection. And now the C part suggests two changes to the apparatus that would increase the initial deflection of ammeter. Okay. Now I am interested to increase the initial deflection. Jivata Pavitra, can you suggest me what should we do to increase the initial deflection? G, Pavitra, can you suggest? We are interested to increase initial deflection as well. Move the bar magnet or drop the bar magnet at a greater height. When you release from a greater height, then obviously it will keep on falling. Speed will be high when it is entering the coil. So you should release the bar magnet at a greater height. Number one. Number two, Pavitra, suggest more. Release the bar magnet from greater height. You should increase the height. Then obviously it will enter into the coil with greater speed. Number one. Number two, use a strong magnet. If you change the magnet, if you change the magnet, then obviously by changing magnet, strong magnet, it will increase the quantity of current. Then obviously there will be greater deflection. Okay. Generator we will study tomorrow, but these two questions I left, and now I am going to explain these two questions by teaching another definition. And what is the definition? So the definition is the heading is motional EMF. So what is motional EMF? I'm going to explain. Consider I have a bar magnet. Consider I have two magnets. One of them I have placed out of the screen. The other one is placed behind the screen. So I am drawing a magnetic field into the page. I am drawing a magnetic field into the page. Magnetic field lines into the page. And now consider I have a metal rod. I have a metal rod, simple metal rod. No battery, no generator, simple metal rod. And now move this rod across the magnetic field. Across the magnetic field. Across means the angle between the rod and magnetic field lines is 90 degrees. The magnetic field is into the page. The magnetic field is into the page, and you can apply left hand rule. Your first finger towards the screen, and now open your second finger in the movement of the rod. In the movement of the rod. Okay. हाँ बेटा पवित्रा, if you apply Fleming left hand rule, first finger towards the screen, second finger towards, sorry, second finger towards the right hand side, then where is your thumb? Pavitra, where is your thumb? Downward. Totally wrong answer. My thumb is pointing upward. If I am using left hand rule, our answer is right. It is upward. If I am using left hand rule, my first finger towards the screen, my second finger towards right hand side, then my thumb is pointing upward. And if my thumb is pointing upward, then according to the rule, electric current is generated in upward direction. When you are moving when you are moving a metal rod, note down this definition, beta. Note down this definition. When a metal rod is moved across the magnetic field, magnetic lines are into the page, and you are moving bar magnet towards the right hand side. It means you are moving metal rod across the magnetic field. Then what happens? Sir, induced current is produced in the rod. Induced current is produced in the rod. Induced current is produced in the rod. And this current is produced due to the movement of the wire. Due to the movement of wire. That is why I am calling this as motional EMF. And remember, the angle between movement and magnetic lines must be perpendicular. Must be perpendicular. And now I am giving you another example. I am giving you another example. Consider this is a magnet, and now this magnet is placed on a horizontal table. Consider this is placed on a horizontal table. Then you know magnetic lines are directed from North Pole to South Pole. So these are magnetic lines. These are magnetic lines. Sir, magnetic lines are horizontal. Magnetic lines are horizontal. And consider this is a rod. This is a green rod. And this green rod is placed on the table. And if I move this rod in upward direction, if I move this green rod in upward direction, then you can see, so the movement is upward, the movement is vertical, the movement is vertical, and magnetic lines are horizontal. Then current must produce in the rod. If you move rod upward or downward, if you move rod upward or downward, when the rod move upward or downward, then current is produced. But if someone moves this rod in this direction, and this direction is parallel to the magnetic field, magnetic lines are horizontal, the movement is horizontal, no current is produced. No current is produced. When the wire moves at 90 degree, then current is produced. If the wire is moving at 0 degree, parallel to the magnetic field, no current is produced. If the wire is moving parallel, if the wire is moving parallel, no current is produced. And now the question is here. Now the question is here. The question on your screen. So the two ends of a metal rod are connected with a copper wire to a sensitive ammeter. The rod is placed horizontally in the horizontal magnetic field. The magnetic field is horizontal. The magnetic field is horizontal. And now the rod is moved upward. The rod is moved upward. Okay, you can see the magnetic lines are horizontal. The magnetic lines are horizontal, and the rod is not moved horizontal. The rod is moved vertically upward. Vertically upward. The question is, an EMF is induced in the rod. The question is, state two factors that determines the size of induced EMF. The question is, when induced EMF is greater, when induced EMF is lesser, so apply common sense. So in this magnetic field chapter, if you use a strong magnet, if you use a strong magnet, then a strong or greater induced EMF is produced. So factor number one, induced EMF size. Size means magnitude of induced EMF depends upon depends upon the strength of magnetic field. The strength of magnetic field. If the magnet is strong, then greater induced EMF is produced. Number one. Number two, this induced EMF is produced due to the movement of the wire. So speed of the wire is important. Speed of moving wire is important. If the wire is moving at fast speed, greater EMF is produced. If the rod is moving slow, then less EMF is produced. So induced EMF depending upon the speed of the moving wire. So these are two factors which I have explained. And now they are asking the size of the current in the ammeter depends upon the size of induced EMF. This question is very, very simple. Current depends upon induced EMF. Okay. State one other factor that affects the size of the current. Ji, beta Pavitra, can you answer me? On what factors current depends? In current electricity, you have studied. Sir, current is directly proportional with EMF or voltage and inversely proportional with the resistance of wire. The size of current, the size of current depends upon voltage, EMF, as well as resistance of the wire, as well as the resistance of the wire. And now the last part of today's class. Now the wire is moved horizontally. The wire is moved horizontally. Nevia, what happens if the wire move horizontally? Nev yes, you are right. There is no current. No current is produced. Okay. So the answer is state, sir, no current, no EMF. Sir, why? Because when a wire moves perpendicular, then wire cuts magnetic field line. When wire moves parallel, it is not cutting. It is not cutting magnetic field lines. It is not cutting magnetic field lines. And when it is not cutting magnetic field lines, then obviously there is no induced current. And now the next part is very simple. They are asking magnetic field lines you have to draw. So you can draw parallel, equally spaced magnetic field lines from north to south pole. And now again the same type question. So there is a north pole, south pole, and now what happened? So the wire is moved vertically downward. The wire is moved vertically downward. So this is the same topic as we have studied in the last question. When it is moved downward, then obviously it is cutting magnetic field lines. Greater speed, sir, greater current, greater deflection in the ammeter. Vertically upward, sir, initially downward. When it is moved upward, then deflection will be opposite. Opposite deflection when the wire moved in opposite direction. And greater speed, so greater deflection. Okay, Buddha, so we have completed this topic. Alhamdulillah, and tomorrow we will start and we will complete AC generator tomorrow.